Okay, so we're going to continue from last time where we have an AVL tree. Remember, we've got all those various rotations that can occur, a left rotation, left-right rotation, right-left rotation. And it's all based on the balance factor, which is the height of the left subtree minus the height of the right subtree. And it becomes unbalanced if it's +2 or -2. And so we're going to go through a full example here. Given all these key values, we're going to insert them into an initially empty AVL tree, a balanced binary search tree. So for the first three, that's pretty straightforward. This is one of our simple examples. I insert 8, I insert 4, but before we continue here, let's make sure that our balance, clearly this is balanced. If you want to rebalance it, you're just going to skew it over to the right. But what were the balance factors again? What's the balance factor of an empty tree? Or what's the height of an empty tree, I should say, sorry. It's going to be -1. -1 minus -1 gives me 0. And what about this? The height of a tree of size 1, of a seed, basically, a single node tree is going to be 0. So 0 minus -1, it's +1. So it's skewed to the left, but only slightly. But when we go to add in node 7, well, that's less than 8, greater than 4, so we end up going over here. So again, we update our balance factors. There's a balance factor of 0. This one gets, should have brought a better eraser. This one now has a balance factor of -1 minus 0, so it's -1. And this one has a balance factor of 1 minus -1, so that's going to be 2. It's skewed to the left, then it's skewed to the right. Positive, negative. So what kind of a rotation are we going to have to do here? A left, then a right rotation. To get something that looks like, well, when we pull 7 up here and pull this all over here, then 7 becomes our new root, 4 becomes the new left subtree, and 8 gets pulled over here. And what are the balance factors on all of these without even going through them? A minus B, A minus C, whatever, right? It's completely balanced, right? All these balance factors are now going to be 0. Okay? Let's continue. We will insert 3. So that gets inserted as a left child of 4. What are the balance factors here? Well, this is 0, right? This is going to be 0 minus -1, so it's going to be 1. This is going to be 0 as well because we didn't change it at all. And what about this one up here? Now since we added to its left subtree, it's going to be 1 minus 0, so it's going to be 1. This gets updated to 1. Okay? We might potentially have to update the balance factors all the way up because of this rebalance. As long as you keep track of the height, and when you insert something, you update the height here, and then you update the height of the parent, you update the height all the way, going all the way back up. But you only have to do it in one direction. All the things over here, all the cousins and all of the distant relatives in that tree, they're not affected by that insert. Right? Only the immediate descendant or ancestors are affected. All right, the next one, 2. Well, that gets inserted as a left child of 3. What are the balance factors now? So this is still 0. This is going to be 0 minus -1, so it becomes 1. This is going to be, what the balance factor here is going to be 1 minus -1, so what happens here? 1 minus -1 is 2. So this gets updated here. And at that point, we stop updating our balance factors because we've already found something that's skewed. This is skewed all the way to the left. Positive, it's skewed to the left. Positive, it's skewed to the left. So what kind of a rotation are we going to need to do to correct it? A right rotation. About 4. Right? So we're not going to affect the rest of the tree. We're only going to affect the tree at which that imbalance is there. So this becomes, if I shift this up, 7 and 8 are unaffected. And 3 comes up to be the new root of that subtree. And we've got 2 and 4 here. All right? Now let's recompute those balance factors. just to get some more practice here. 0 and 0, and of course 0. Now the balance factor here is going to be also 0 because it's completely balanced. The balance factor here is going to be 1 minus 0, so 1, you see it was unaffected. It was unbalanced here. We didn't need to continue updating it upward because we changed it. By changing it, we rebalanced it, and so it's unaffected up here. Okay? Next one is going to be 5. So where does 5 go? Less than 7, greater than 3, greater than 4. So 5 gets inserted over here. Balance factor of 0, balance factor of negative 1 minus 0, so negative 1. Balance factor here, what about this? 0 minus 1, so it's going to be minus 1. This is unaffected because height is with respect to downward orientations, so we don't have to go back down here and recompute balance factors. Let's come up here though to the root, and we might need to update the balance factor here. This is 1, 2 minus 0, so what happens? It gets unbalanced at the root now. So it is positive, this is a positive 2, 2 minus 0. Positive, negative, what kind of a rotation are we going to have to do now? So it's unbalanced to the left, then it's unbalanced to the right. So I need to do just the opposite, a left, then a right rotation. What does that look like? Let's go with that in 2 steps. Okay, here's the intermediary step. Here's the left rotation. What happens is I bring 4 up. 3 becomes its new subchild. 2 is still hanging off of there. 5 is over here. And I've got 7 and 8. Note that I'm not drawing the tree fully here. This is an intermediary step. And then I do a right rotation. So I bring 4 up to become the new root. 7 comes down with it. 8 is still hanging off of it. 3 gets up with it. And 2 is still hanging off of it. But what about 5? 5 is basically that tree. Remember the generalized left-right rotations, right-left rotations? Sometimes trees have to swing over. And in this case, it swings over to become the new left child of its grandparent. Here's the grandchild, parent, grandparent. It needs to become the new left child of it, and so it's over here. It's swung over to become the left child of 7. And really, that's the only place that it could belong. 5 is greater than 4, and it's less than 7, so it has to go over there. 1, where does it go? Right here. Let's recompute the balance factors. 0, 0, 0, 0. This one is going to be 0 minus negative 1, so 1. This one is going to be 1 minus negative 1, so 2. And it's unbalanced right there. So what kind of a rotation are we going to do? A right rotation. And we end up with 4. 2 comes up to the new root of that tree. 1 and 3. And then everything else is unaffected by it. We've got 5 and 8. And without even thinking about it, tell me about all the balance factors of that full binary search tree. They're all 0, right? Because it's all perfectly balanced. There are no gaps. There are no missing elements. Continuing with the last ones, 10 and 6 get inserted. Now that does make some of the balance factors non-zero now because it is, switching. It is affecting the topology of the graph. But is it any unbalanced? Is there any, without even knowing left-right rotations, is there any way that we could rearrange these so that it was more balanced? Well, we could put one of them over here or something like that, but this level is not full. We don't have a level going down that is unbalancing with those other levels. Nothing's going to affect this. Right? So let's go ahead and look at the balance factors. 0 and 0. Negative 1 minus 0, so this is going to be negative 1. Likewise, this is going to be negative 1. What about this one? 1 minus 1, 0. 0, 0, 0. And 1 minus 1, 2. So it's going to be negative 1. Right? Let's add some more. Right? And unfortunately, I didn't leave enough gaps here, so we're going to have to add in fractional values. What I want to do is I want to fill up the right subtree. Okay? Here's a practice, though. What could I put in this node here that would make it a valid binary search tree? Has to be greater than 4. Has to be less than 7. So already I'm between 4 and 7, right? Has to be less than 5, so it has to be between 4 and 5. I'll go ahead and go with 4.5. Likewise here, what could I put here? 7.5. All right. Now, what I want to do, I just fast forwarded because what I wanted to do is I want to make this subtree right here full. This subtree over here is not full. It's got 4 missing nodes at that level. I'm going to cause an imbalance. Let me go ahead and hang something off. It doesn't really matter where or what. What could I put there, though, as a left child of 6? It has to be greater than 5 and less than 6, so 5.5. There we go. Now let's look at the balance factors for this. This is 0. This is 0, this is 0, 0, 0. What about this one? This is going to be 0 minus -1. So this one gets updated to 1. What about this one? 0 minus 1, so -1. What about this one? 1, 2 minus 1, so 1. That does get updated. This is why you have to go all the way back up to the root, potentially updating those balance factors. What about this one right here? 1 minus 1, 2, 3. 1 minus 3 is going to be -2. -2 indicates the negation indicates an imbalance which direction? The right. I go down to the right subchild and it's positive, so that indicates an unbalance in the left direction, and that's exactly where we put it. So it is unbalanced to the right, then to the left. So what kind of a rotation are we going to need to do to fix this? If it's unbalanced to the right, left, we need to go left, right. So, right? I think it's going to be right, then left. Is that right? What were the notes that I gave you yesterday? I forget. I think this is right. So let's go ahead and go with an intermediary step here. I don't have this in the notes by the way, so I might be screwing this up. I don't know. Let's go ahead and try it anyway. 4, and then you still have 2, and 1 and 3 here. No, okay. If this ever goes out, let me know, because I don't think it'll be recorded. It sounds like it was going out. I just want batteries are fine. Yep. All right, we're fine. So when I do a right rotation here, 5 comes up to become the new subchild. Along with it comes up 4.5, and 6 and 5.5 are temporarily orphaned. Right? 7 gets pulled down over here. And then 8 is still hanging off of it with 7.5 and 10. Right? Again, this gets temporarily orphaned because we pulled this up. Now we do a left rotation, and 5 becomes the new root. Now let's reorganize this tree here. When that happens, 2, 1, and 3 all get pulled down. All right? Let's see what else happens. Oops. Say what?
Doesn't 4 go between 2 and 5 then?
Oh, I was going to say, thank you. I was going to. I thought I just drew myself into a corner here because I thought, what's going to happen with 4.5 here? So this gets pulled up, and what happens? 4. There we go. And this one then gets orphaned. Remember, it's like T2 or whatever. This is T3, T2, and T3. And what happens is this one gets swung over to become the new right child of 4, so 4.5. And then, of course, 2 is still hanging off of that, and 1 and 3. There we go. When this gets pulled up, 7 is still the right child. 8, 7.5, and 10 are all still hanging off of it. And now what happens to this orphan tree over here? 6 with a child of 5.5. It becomes the new left child with still 5.5 hanging off of it of 7. And you can see that it's all now fixed. And we've got everything balanced again. All the leaves, of course, are going to have a balance factor of 0. This is balanced, this is balanced, this is balanced. What is the balance factor here? It's going to be 0 minus negative 1, so 1. This is going to be 1 minus 1, 0. And then, of course, you can see that these two subtrees have the same height, so this is also going to now be rebalanced. And the entire tree is, oops, I forgot this one. This is going to be 1 minus 0, so 1. Right? That one was not in the notes. But of course, if you're trying to check your work, there are plenty of AVL tree simulators online that you can go ahead and check out. Instead of doing it on a piece of paper like this, you can, well, I mean, for your assignment, of course, you'll have to write it out on a piece of paper, but you can always check it with a simulator. Okay? We're not going to go through a full analysis of this, but I will tell you that there are bounded AVL trees, or AVL trees. They have a guarantee that the height is bounded above and below. Of course, the height is going to be bounded below by logarithm, and I think the floor. That's kind of a trivial lower bound. But as we've seen with general binary search trees, or binary trees in general, you have no upper bound other than order n. n minus 1 is going to be your height, right? But with AVL trees, there is a nice little bound here, 1.4405 times log base 2, of course, n plus 2 minus 0.3277, right? And this is just a mathematical analysis of assume everything has a balance factor of -1, 0, or 1. What is the absolute maximum that the height could be? And basically, because it's bounded below and it's bounded above by logarithm, then we can say that the height is going to be theta of log n. Okay? So therefore, all operations are order log n. And we've finally reached a satisfying conclusion of having a collection data structure that can hold stuff with efficient operations on everything, right? Think about you're starting in CS1. We cover binary search. That's just a dumb data structure. It's just an array. But if it's sorted, then you can exploit that sorting by doing binary search. But can you do arbitrary insertions? No. If you need to do an insertion somewhere in the list and maintain that order, then that means that you've got to scoot everything down. Right? You have to potentially copy n things down. So efficient search, but inefficient insertion and deletion, of course, because if you delete it, you don't want these gaps in your array. You need to shift things down. And then we started looking at binary trees. Well, binary trees offered kind of like that, but and then the other drawback to binary search and using arrays is that static arrays allow you to binary search requires that you have access to random access. In other words, you can jump to the nth element with just a memory offset computation. Right? With a linked list, of course, you can't just jump to a position. You have to start over here and perform n traversals to get to the center or something like that. But the trade-off is that a linked list, you can insert stuff at one end or the other end in constant time. So efficient search, efficient insertion at particular areas of the list, but inefficient searching. Then we introduced other list-based data structures like stacks and queues that offered that exploited that structure so that they had efficient, though restricted access kind of data structures. Then we looked at trees, and trees offered, if they were balanced, a way to retrieve, insert, and update and delete, all with respect to the depth of the tree. And in the best case, the depth of the tree is going to be log n. But we still needed more structure. We needed a way to guarantee that the tree was going to be remaining balanced with all these operations. And now we're finally there. You can insert stuff, you can retrieve stuff, you can delete stuff, the three basic operations of any collection data structure, all in order log n. Okay? And as I said before, there are at least a dozen different balanced binary search tree implementations, all based on other ideas. I'm going to show you one more, just to show you that there are a variety of ways of doing these things. This is a very restricted version of what are called B trees. B trees are used commonly in database implementations. So if you open up a database implementation like MySQL or something like that, more often than not, you'll find a B tree implementation because they're nicely tunable for cache misses and cache hits and disk operations and stuff like that. We're going to look at a restricted version of this called 2-3 trees. Right? You can have 2, 3, 4 trees. You can have 2, 3, 4, 5 trees. You can have, in general, just B trees, which is a generalization of these things. Okay. Every node in a 2-3 tree now has at most 3 children. Right? It could have 2 or 3 children, except for, of course, leaves. And leaves have no children, but they're not going to have 1 child, right? And 0 children, 0 children is going to be a leaf, and 1 child, DNE, does not exist. Right? Well, to have 3 children, you need a different structure. There are 2 nodes which contain 1 key and 2 children. This is just a regular old binary search tree node. If you've got k over here, then this is less than k. And if you've got over here, it's going to be greater than k. So its left child is going to be less, its right child is going to be greater. And the only other possibility here is a 3 node. A 3 node has 2 keys that all label key 1 and key 2. And key 1 is less than key 2. And 3 children. So you can imagine what that looks like. I'll draw it as kind of an array here, because that's how it's usually done. K1 and K2. Well, if it has 3 children, then tell me about the relative ordering of each one of these keys. Everything over here in the left child is going to be less than K1, and by transitivity, of course, less than K2. Everything over here in the right subtree is going to be greater than K2, and again, by transitivity, greater than K1. But what about everything over here? Everything over here is going to be between, right? I'll call this A. This is going to be at least K1 and at most K2. Right? And these could be 2 nodes or 3 nodes. And you could have 2 nodes, 3 nodes all over the place in the tree. Another property is that all nodes are, let me go ahead and rephrase this. The tree is full in the following sense. Not everything is going to be like a 3 node containing 3 children, but that could be very, very full if you want to call it that way. That. But the tree is full in the sense that all leaves are at the same level. Okay. So how does this work? How does insertion work? I'm going to give you a high-level description, and then we're going to go along with an actual example. Insertion is always done in a leaf. Okay? So let's look at an example here. I'm going to go ahead and insert those same values. I'll go ahead and write them again so that we have them. 8, 4, 7, 3, 2, 5, 1, 10, and 6. Okay? Well, let's go ahead and insert 8. Well, into an empty binary tree, then this becomes a 2-node with no children. Okay? Now, let's insert 4. Well, it's always done in a leaf. How many leaves are here? The root is a leaf because it's a seed, right? So the second step here is that this becomes, from a 2-node, there's real estate in there, right? We can fit another key in there. So let me go ahead and put in 4 and 8. And that 2-node now becomes a 3-node, right? So if inserted into a 2-node node, then it becomes a 3-node. Right? And we never have to worry about the children when it becomes a 2-node into a 3-node, because remember, it's always done in a leaf. A leaf by definition has no children, so we don't need to worry about anything down here. Okay? All right, next step. Temporarily, what happens is that we've got 4, 7, and 8 all in the same node. Now, is this a 2-node or a 3-node? No, it's full, right? We need to get rid of somebody. Who could we get rid of? 7. I like that candidate. We'll go ahead and get rid of them, not by pushing them down, but by pushing them up. So when it becomes full, what happens is that 2-node that 3-node becomes a 2-node, and the middle element, the median element, gets promoted. So it ends up looking like this: 7, 4, and 8. Right? So if inserted into a 3-node, then the middle element is promoted, and the other 2 nodes split into, I should not say nodes here, but keys, into 2 nodes. Right? 4 and 8, those are 2 nodes now. And we've got a regular binary search tree here now. Right? So let's go ahead and continue. When I insert 3, I come down here to 7. 3 is less than 7, so I come down here, and this is a leaf now, and it's a 2-node, so it becomes a 3-node. And it looks like this. 7, 3, and 4 are now in a 2-node, and 8 is unaffected. Now let's insert 2. Okay? 2 comes into to 7. Okay? It goes down to the left, and this is a leaf, so we end up inserting it here temporarily. All right? 7, 8, and ... What we've got down here temporarily, we've got an overfull node: 2, 3, and 4. So again, if it's inserted into a 3-node, the middle element gets promoted up, and the other 2 keys split into 2 nodes. So what does that look like? 3 gets promoted up here. That 2-node becomes a 3-node. 3 and 7. And then we've got over here, here, and here. Remember, 2 and 4, they get split up into 2 nodes. So 2, 4, and 8 remains unaffected over there. All right. Now we can also fast forward here. What happens to 5? It gets inserted here, making it into a 3 node. 1 gets inserted over here, making it into a 3 node. 10 gets inserted over here and making it a 3 node. And now we've got a full tree again. A very full tree, if you, I don't know if there's a term for it, but a maximally full tree. What did I say? 2, or 1 and 2, sorry. 1 and 2. Over here we've got 4 and 5. And over here we've got 8 and 10. All right? Now, 6 comes in. It's between 3 and 7. So it comes down here. It's inserted as a leaf here. So what happens when we insert 6 here? This becomes over full. Which one do we end up promoting up? 4, 5, 6. We end up promoting up 5. But what happens there? That becomes a over full node. And so we end up having to promote until it looks like what? When we promote this, we get something that temporarily looks like this. 3, 6, and 7. And then 1 and 2 over here. 1, 2. 6 got promoted up, so we've got 4 and 5, right? Oh, sorry. Dang. 5 and 6. And then 8 and 10. Temporarily, this has 4 children. Can it have 4 children? No, because it's a 2-3 tree. So what happens again is that this gets promoted up, these two get split up, and now these only have 1 parent. So it ends up looking like 5, 3, 7, 1 and 2 as still a 3 node, 4, 8 and 10 still as a 3 node over here, and then 6 is over here. Right? And then you can continue like this. The promotion at a leaf, when a leaf gets over full and it promotes up, it might end up promoting it all the way up to the top. Right? And a B tree is simply just a generalization of this. Instead of allowing 1 or 2 keys per node, it allows up to m keys and a minimum of m, or what is it? There's a bound on it. It's a I don't have it, but there's a minimum number of keys and then a maximum number of keys, right? And so you could go ahead and tune this to say an array that can be held in a single page of data, so that you can minimize cache misses and cache hits with disk space, right? And that's why this is used a lot in database implementations, because it's efficient. You've got order log n operations everywhere, which we'll talk about here in a second. But also it's tunable to your system's memory model, right? So that's how 2-3 trees work. Let's go ahead and analyze this, okay? What is the minimum size of a 2-3 tree of depth D? And what is the maximum size of a 2-3 tree of depth D? Right? I want to get a bound on these, because if I've got a bound on D, then basically if I can show a lower bound of logarithmic and an upper bound of logarithmic, then I've proven that this is a balanced binary search tree. Everything is done with respect to depth. You always insert into a leaf, so you start at the top and you go all the way down to a leaf. Insertion is going to be proportional to the depth. Removal, we'll talk about that in a second. Search is also going to be proportional to the depth, right? And it's pretty straightforward how you do searches on 2-3 trees as well. It's just an extra check. Here's the thing that I'm searching for. Is it less than the first key? Okay, go that way. No? Okay, well, is it less than the second key? Okay, go to the center. Oh, is it less than, or is it greater than the second key? Then go that way. If it's a 3 node. If it's a 2 node, then you just have different logic. So check what type of node it is. Or if it's done as an array in general, then you can just go, is it greater, is it greater, is it greater, is it greater, and that tells you where you go next, right? But I need to get a bound on the depth here. So we've already actually done this part. What is the minimum size, n, of a 2-3 tree of depth d? Remember, they're full. So I have a tree of depth d, and by minimizing the number of keys in there, basically I'm saying assume that everything is a 2-node. In other words, it's a regular old binary search tree, or a binary tree, but it's full, right? Say that it's of depth d, ... right? How big is it? Or how many nodes are in there? Remember, at the first level there's 1 node. At the second level there's 2, 4, 8, ... In general, at depth I, or depth d, it's going to be 2 to the d. What's the summation of all of these things? 2 to the I running from 0, right? 2 to the 0 up here, up to d is going to be 2 to the d plus 1 minus 1. Right? That's the minimum size. So the answer here, we've already done this, 2 to the d plus 1 minus 1. Now it's not that, it's the exact same analysis for assuming that everything is a 3-node. Right? So let's go ahead and draw this again. I've got one node up here that's a 3-node, and it has 3 children. So there are 2 keys here. Right? There's 1 node, and a number of nodes, number of keys. Right? It's just twice over. Right? There are 2 keys in this one, then there are 3 children. So there are 3 children here. Well, how many keys are here? 2, 4, 6. Right? How many nodes are in the next level? 1, 2, 3, 1, 2, 3, 1, 2, 3. How many? Oops, should have drawn them deeper. There we go. They're going to be 9. Right? And how many keys? 2 each, so 18. Right? So in general, at depth d, how many are there going to be? What's the progression here? 3 to the, right? These are powers of 3 now. 1, 3, 9. What's next? 27, 81, 243, et cetera, et cetera. So this is going to be 3 to the d. Well, and then how many of them are here? Well, just twice over, 3 to the d. So what's the total number of keys here? Right? Each one of these is just multiplied by 2. So it's 2 times the summation of 3 to the I running from 1 up to d. Right? Help me out. What's this geometric progression right here? If you don't help me out, I'm going to have to look it up. I think it's, yeah, okay. It's going to be 3 to the d plus 1 minus 2, I believe, all over, I think, 2, with our 2 still out front here. Is that right? Oh, no, it's going to be minus 1. All right, there. All you have to remember is the general form of this. I running from 0 up to n of x to the I is going to be, now this is what I need help on. What is the general form of this? I think it's going to be x to the I, to x to the n plus 1 minus 1 all over n, or x minus 1, right? All over x minus 1? Question mark here. Does anybody remember their geometric series? Identities? All right. Well, that's why I'm going to put a question mark there. I think that that's what it is. But in any case, it does simplify here. These 2's cancel out. So you've got 3 to the d plus 1 minus 1. Right? And I am pretty sure about that. I think those 2's cancel out. I don't remember. In any case, take this one and this one. Let me rewrite it over here. In my notes, what I've got here is that that the depth d is, n is, so how do I want to do this? 2 to the d plus 1 minus 1. That's a lower bound on n. And then an upper bound was, I did forget a 2 there. 3 to the d plus 1 minus 1. There we go. Okay? That tells me that this is at least as many keys. This is the number of keys. And this, of course, is the depth. So what I want to show is that I want to solve for the depth here. I don't want to bound. I came up with a bound on the number of keys so that I could eventually come up with a bound on the depth. I want to show that the depth is order log n, right? So otherwise, there's no point in doing this, right? So I need to solve for d over here and solve for d over here in 2 equations. I get that 2 to the d plus 1 minus 1 is less than or equal to n. Let's go ahead and solve for that one. What happens, we've already done this. You take n to the, n plus 1 log base 2 of n and then plus 1, minus 1, there we go. And the depth is less than or equal, I take the d on the other side, right? I just have to think about that for a second. Yeah, because d was over here. There we go. We're good. All right. And then what about this one? N is less than or equal to 2, 3 to the d plus 1 minus 1. All right. And solving for d gives me n divided by 2 over to the other side plus 1. Oops. And then I will take a logarithm of that, but it's not log 2, it's log 3, right? Minus 1. And that's less than or equal to d. There. So I've got a lower bound on d, and I've got an upper bound on d. So altogether, that's why these kind of flip when you solve for it, because now you're doing it with respect to d here. So d is less than or equal to log base 2 of n plus 1, which is all I really needed, actually. But I'm also establishing a lower bound here of this log base 3 of n divided by 2 plus 1 minus 1. So therefore, if you've got a lower bound of a logarithm, and all logs are the same to within a constant because of the change of base formula, you've got that d is theta log n. You've got it bounded below, you've got it bounded above, both by logarithmic functions. Okay? Now let's reverse and go back over here and rewrite this, that this should be question mark, definitely question mark now, but there should be a 2 out front here. There we go. Okay. Any questions on balanced binary search trees? Like I said, there are a dozen or so other implementations. There are red-black trees, there are treeps, there are B-star trees, and a bunch of other things. Each one of them with a little slightly different variation on it that might give you other properties that are desirable for your particular application. By the way, popular programming languages. Java, for example. Does Java have a balanced binary search tree implementation? You never implement your own, right, in practice. Java has a tree set. Is that the interface, though? Or I'd have to double check. I don't have it here. Is tree set the interface, though? Or is it a set interface? Okay, so tree set, this is an implementation. The interface is a, what did you say, sorted set?
Yeah.
There we go. Parameterized by this. And I believe that it's a red-black tree implementation. And honestly, I do not know, but most of you are using Python. Is there a balanced binary search tree implementation in Python? I would tend to doubt it, because the Pythonic way of doing things is a little bit different. I'll put a question mark here. The Pythonic way of doing things is to instead use hash-based data structures, which is what we're going to look at here with the rest of our time. Okay? So you can, in Java, you've got a red-black tree implementation. Python, does anybody know? You could Google it really quick, and does Python have a balanced binary search tree, an AVL tree implementation? I'd probably just search for balanced binary search tree because it may or may not be AVL. It could be something else entirely. But that's not the Pythonic way of doing things. The Pythonic way of doing things is to use I don't want to say an even better data structure because it does have limitations. There's no perfect data structure. If there was one data structure that offered efficient operations everywhere and also all the properties that we would ever want, then there would be no need to have lists, stacks, queues, binary search trees, heaps, et cetera, et cetera. Instead, they're used in different applications. Right? If you have need of constantly updating and inserting stuff, then maybe a balanced binary search tree is better. Right? Otherwise, what Python tends to use are hash tables. Hash tables. Right? So hash tables offer amortized constant time, that is order 1 operations. Now this word is the big caveat here. If I covered that up and I told you they're all constant time operations, we're done, right? We can cut out half of CS1 and CS2 because all we ever need is hash tables. And to level with you, if I'm ever doing any work, hash tables are my to-go data structure because all around they are the best data structure to use. You know them better in Python as what? In Python, what do you have? You have lists, you have sets, you also have dictionaries, right? Dictionaries are basically hash tables. But the key word here is amortized. In other words, if you look at the behavior of the data structure over the lifetime of the data structure, over the long term, over your entire program's run, then on average it tends to look like it's constant time. But in reality, what you have is if your hash table gets too big, you have to reorganize it so that you have this constant time operation. And that's what means that you have to rebuild the entire hash table over and over and over again. These spikes in inefficiency, right, are you can look at them as if the hash table gets too big or too full, then you have to rehash everything. So you've got something that looks very, very constant until you get to, and the performance degrades. So I'm going up here, this is time or resources. And then you say, okay, that's too much. Let's go ahead and delete that hash table, rebuild it. It spikes because that is extremely expensive. But then it goes down again, right? And then over the lifetime of your data structure's lifetime, then it looks constant until it starts getting worse and worse and worse because it's fuller and fuller and fuller, and then it spikes again because it reorganizes itself so that it can get the performance back down here. How does that work? Well, elements are stored in a regular old array, right? Regular old array, that's where they're stored, right? But elements, the elements location is determined, that is, its index is determined by a hash function. So what is a hash function? First of all, what's a hash? Social media, you know hashes. What is a hash? You ever get into the thought hashtag, right? Well, that's because that symbol is usually called a hash. Why is that symbol called a hash? Think of your pen not as a pen, but think of it as a knife. You cut, 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 cut. You're hashing something up. What else do you hash with a knife? No? What do you have for breakfast? Hash browns, right? What are hash browns? Hash browns are potatoes that have been hashed up, cut up. So hashing is nothing more than taking something large and cutting it up, right? A hash function maps, it's a function, so you've got a mapping, maps a large domain to a small codomain or range, right? You can look at it like this. There's a big domain over here, and then there's a much smaller finite codomain over here. And so you're necessarily mapping something big, say even infinite, down to something small. The way that you end up doing it is by taking the domain and hashing it. Right? This section, everything in this section, say, gets mapped to this one element over here. Everything in this section gets mapped to another element over here, et cetera, et cetera. You are hashing up the domain into the small codomain. Right? Remember, this is domain of a function. This is codomain. Okay? Here's an extremely simple hash function. Here, an extremely simple example would be, say, h sub x is equal to x mod 7, let's say. Right? Now, what kind of a hash function, what does that hash function look like? What is the hash of 17? All you're doing is taking the remainder here. This is modulo. If you're more comfortable with it, the percent sign in most of your programming languages. It's just taking x, dividing by 7, and then giving you the remainder. Okay? So if I take 17 and divide by 7, what's the remainder? 3. Right? Here's another one. H sub 23. What's that hash value? 2. Okay. What about h sub, I don't know, 28? 28 divided by 7, what's the remainder? 0. Right? What about 29? What's the remainder of that? 1. What about 20? I should have gone backwards here. What about 27? 27 divided by 7. 7 goes into 27 3 times with a remainder of 6. Dot, dot, dot. Right? Let's go ahead and go with one more here. What if I did h sub 24? What's the remainder of that? 3. Uh-oh. What do you observe here? H sub 17 is equal to h sub 24, but 17 is not equal to 24. In other words, what does the hash function look like over here? In this, here's the codomain, and here's the domain. Right? It's much smaller. This particular example, these two things get mapped to the same thing. So what can you conclude about hash functions? Because they're mapping something large to something small. What property is this not? Remember functions? It is a function, and functions can be injective, surjective, or synonyms of those would be onto and one-to-one. Is this one-to-one? Nope. So it is hash functions are not one-to-one. Right? As a consequence, mappings, different values may map to the same value. Right? We call this collisions. Those two elements have collided. This is a collision. It's a hash collision. Okay? So that's one thing that we're going to have to remember. But does this fit the bill? Does this map a large domain down to a small domain? What is the domain over here implicitly? What have I been talking about the entire time? H is mapping, what is that thing? It's all the integers. It's mapping all the integers to the, code, what did I do? Domain, codomain. There we go. How big is the codomain? 0, 1, 2, 3, 4, 5, 6. Right? There are elements that can get mapped to all of those. So it's a finite codomain, 0, 1, ... up to 6. We call that thing Z mod 7. Right? So if you've got all the integers mapping to just 7 of the integers, obviously then you are mapping a large domain, an infinite domain, down to a small domain, a finite domain here, that's only of size 7. Right? This is Z mod 7, right? And it consists of 0, 1, 2, 3, 4, 5, 6. So if I write Z mod M, right, in general, Z mod M, then this is the integers 0, 1, 2, ... up to M minus 1, because those are all the possible remainders, okay? Well, that's a hash function. How can we map hash? Remember, the whole point of this is to have a data structure that holds things. In other words, we want a hash table to hold objects. It doesn't matter if this is Java, Python, or whatever programming language you want. You want to hold objects, okay? So an object, we're not always going to be holding integers, are we? But same tricks as we've used before. We're going to, as a first step, without loss of generality, you can map objects to integers. Right? In Java, how is this done? Remember, hopefully you've used hash maps before, right? And now you know why they're called hash maps, because they're a map that is backed up by a hash table. Well, how do they work? I've got an object here, say a student object or a node object or something that I want, and I put it into a hash table. How do I map that object to Z here in Java? Anybody know? You ever played around with the hash code method? Right? That returns an integer. Right? That's the return type. What about Python? No, all right. Python, I think, I'll put a question mark here. I think that there's a hash method, self, something like this. Yes, no? Anybody confirm? I think so. In Python, by the way, in PHP they call them magic functions or magic methods. What does Python call these things? They begin with an underscore, underscore, and underscore, underscore here. Basically, they're built into the language that everything will have a default value of this, or that the mere fact that this exists means that it's hashable, and so you can put it into a hash table. You can put it, do a bunch of things with it. Is it hash? Yes? Yeah. Okay. And what are these called when they have a special name, underscore, underscore? They're magic methods, or what are they called? Like if you want a two-string method, for example, str of self, Somebody said it, what? Constructors are like that, but construct, right? I'm looking for the word that collectively refers to all of these. I forget what it is. Right? Oh, is it magic? Okay. They use the same term, magic methods. Right? So in other words, without loss of generality, every programming language worth anything is going to have some way that you can take generic objects and simply map them to a bunch of integers, so that now you can deal with hash functions. Why do you want that? Remember, generally what does a hash function do? A hash function is going to map z down to some z mod m. Why is that helpful? Remember that z mod m is going to be 0, 1, 2, ... m minus 1. What can we use these as? If I take an object and map it to an integer, and map that integer to something in the range of 0 up to m minus 1, then how can I take advantage of this? I will treat these as indices of a regular old array. Right? And now you see the magic of hashing, right? It conforms to the way that computers work. They store things in memory, and they store things in memory all contiguously. Well, I don't have to search through and say, all right, I'm looking for this object here. Look here. No, that's not it. No, that's not it. Well, it's sorted. Okay, I can use binary search. Jump to the center and then search for it, right? Logarithm. Or I can bring in a hash function and immediately jump not to the center, but to the location that it's at. Right? And that's the advantage of a hash function, that hashing, that is, finding the location of an object, is potentially order 1, constant time. I say potentially here because there are some caveats, right? And another thing to observe here is that, well, the clear question is, if you've got the object, in order to compute its hash code and then to find its index, why are you searching for the object? You've already got it, right? No, what you're going to use is you're going to use this as a key. The key maps to a hash code. The hash code maps to an index location, and at that index location is stored a value. Right? So really, the hashed object is going to be used as, typically, it's used as a key to map to a value. And this is why in Java we've got a hash map, or just map in general, that maps a key to a value. Right? You can do, I believe, do this in Python with. Can you do this with dictionaries? Dictionaries support arbitrary objects? I think so. In Python 3. Python 2 and certainly older versions, you could not do this because dictionaries were basically just neutered hash tables. Neutered hash tables because typically the way that you use dictionaries is that you can map an integer to an object or a string to an object, because integers and strings, they had built-in hash values. At least in the latest versions of Python, I don't know how many years it goes back. I don't want to call it new because I don't think it is new. But you can make your objects hashable, so that you can use them as keys to jump to a location and find that thing. Okay. All right. I still don't like the way that they did it, but I really like the way that Java has done this. But that's neither here nor there. Right? That's just a personal preference. So what's the caveat? Why doesn't this always work? Okay. So let me go ahead and create a hash function here. And now we're just going to deal with integers, because I've already explained how you can use objects to map to integers, to map to indices, to map to objects. Let's just go ahead and consider integers here. Let me give you another hash function here. It doesn't have to be just something mod something. It can be a linear function mod 8. Okay? So I've changed x here with k to drive home the point that it's a key. So with mod 8, implicitly, how big is my hash table here? Mod 8, I've got 0, 1, 2, 3, 4, 5, 6, 7. There are going to be 8 elements in my hash table, in my array. 0, 1, 2, 3, 4, 5, 6, 7. Okay, let's start hashing. Let's go ahead and hash the values 10, 16, 4, 13, 86. Okay? So 10, all I need to do is put it into this hash function. That's going to be 7 times 10 plus 13 mod 8. 70 plus 13, 93, mod 8 is going to be 7? No, 3. There we go. So I immediately jump to index 3 and put 10 in there. Okay? Hash of 16 is equal to 7 times 16 plus 13 mod 8. There we go. 70, 112, 125. So 25, 80, 45. Yeah. 8 sub 4. Thankfully, that's easy. 4 times 7, 28. 41, so that'll hash to 1. 4. Okay. And by the way, how are we going to look these things up later on if we need to? We recompute the hash, jump there, and oh, well, there's 4, right? Hash value of, 4. Well, I did that in my head, I guess that's why. 13 is equal to 7 times 13. That's going to be 91 plus 13, so 104. Mod 8. It's going to be 0. All right. Let's come over here. H of 86 is going to be 7 times 86 plus 13 mod 8. And I'm not even going to try to do that in my head. I'm just going to look at my notes. There we go. All right? All good so far. Right? Well, our array is starting to fill up, right? But we've still got plenty of room. Right? So we can go ahead and keep hashing stuff. When it gets full, of course, now we've got a problem. If it's a full array, then we know, with an array list, remember, an array-based list, if your array list gets full, what are you going to have to do? Create a new array of a larger size, copy everything over. We're going to have to do something similar here with the hash table. But not only that, we've got another thing that we have to take care of. Let's add in one more element, 100. This is 713 mod 8. Help me out. What is that? 1. Uh-oh. I want to insert 100. What happens? Can I? Nope, it's already occupied. So reject it. Rebuild it. Right? Remember what this was called? It's a collision. So we might get a lot of collisions. We don't want to have to rebuild this table every single time we have a collision. We need a way to resolve collisions. Collision resolution. So one way of doing this is linear probing. Right? So if a cell is occupied, go to the next cell. until you find a free one, an unoccupied one. All right. Well, for this solution, okay, well, that's full. Go on to the next one, 100. Okay. What happens if we try to do 108? 108, 7 times 108 plus 13 mod 8. What's it going to be? Why did I choose 108? It's just 8 more. It's going to be what? 1? Yes? Anybody confirm my math? 7 times 108 plus 13 mod 8 is 1? Nobody has their computer going? Come on, help me. Well, that probe is going to fail. We fail again. We fail again. And then finally, we find an open spot. Was I correct? I just want to make absolutely sure. Yes? Okay, thank you. I'm not going insane. And what's the next one I could try? H is 116. I'm just going up by 8 because of the properties of mod 8 here. Right? And if I do 116, then I end up probing 1, 2, 3, 4, 5, and then finally, I find an open one. Right? In the worst case, when this gets very full and there's only one left, how many probes do I have to do? How many rehashing values do I have to do? How many comparisons do I have to do to see that it's occupied and you have to go to the next one, next one, next one? So this, say that they're all occupied except for the last one. And I hash it over here. 1, 2, 3, 4, 5, 6, 7, and then finally 8. Okay, that's where it belongs. In other words, if you've got a very full hash table here, it grinds to a halt. It's no better than linear search, right? So if you've got a full hash table, then it starts to get really, really messy, and the performance degrades. Or another way of looking at it is, as it gets fuller and fuller and fuller, the time required to insert stuff and retrieve stuff starts going up and resembling a linear function. Right? At which point you need to say, stop, let's go ahead and reorganize this. And we'll talk about that in a second here. But before we do, let's think about some other collision resolutions. You could do a linear function probe. Where you don't just go over by 1, but you could go, say, hash of k is equal to hash k prime is equal to the previous hash function. You're rehashing it basically, plus some constant L mod m. Right? So instead of going over by 1, 1, 1, you could go over by 5, 10, 15, right? You could do a bunch of skips. Or you could do quadratic probing. Basically, you're just coming up with other functions and seeing what works, right? You could, in general, it's just going to look like 8 sub k I is equal to 8 sub k, the original one, plus some quadratic function plus c2 I squared mod m. Instead of adding a constant, you're adding an entire linear function, right, to the original hash function, right, et cetera, et cetera. So you could come up with all these wacky rehash functions. And usually what works is if you put primes as your coefficients, that tends to work best in practice, because if you use primes, that's definitely going to be relatively prime to m, and you don't get periodicity, right? If you chose m to be even, and then you had an even hash function, it would always go 2, 4, 6, 8, and then wrap around to the exact same ones. You would get caught in a loop, basically. and never explore all of them. And so in practice, you choose these to be primes. Alternatively, what you could do is chaining. Right? Cells can be other data structures instead of one object. All right? So, for example, they could be linked lists. Let's go back to our example, right? And let's rewrite it really quick because I don't want to rehash everything. 0, 1, 2, 3, 4, 5, 6, and 7. And at one point, it looked like this, that we had 13, 4, or sorry, it'll look like this now. Instead of one element, it's put into a data structure like a linked list. 4. And then what was it, 100 over here? And then 10. 16 was in 5. And 86 is over here. And now when we go to insert 108, 116, 124, etc., all we do is compute one hash function value and then go to that data structure and start chaining them together. This is why it's called chaining, right? A linked list is a chain. So 108, then 116, and then you can keep going. 124, ... right? And if you get something that maps to 5 or that hashes to 5, right? You can go ahead and add that. In other words, all of these become a bunch of linked lists. Right? Now that is one way of doing collision resolution. You never have to worry about it again, right? So why don't we just do this all the time? And by the way, alternatively, these could, instead of linked lists, you could use linked lists. What's another thing that you could use? A binary search tree, right? Or an array-based list. Or wait, what about this? What about another hash table? A hash table of hash tables. Of hash tables, of hash tables, of hash tables. Is that going to buy you anything? If I had a hash table of size 8, and then I attached hash tables of size 8 off of those, that's just added complexity. Why don't you just have a hash table of size 64, right? 8 by 8? Then probably not, right? And usually, I've never really even seen an implementation with binary search trees, but, well, no, I take that back. I have seen one, but generally there are some other data structures. But does that buy us anything in the long term? Right? What difference does it make if everything hashes to the same one and you've just got a big giant linked list? Or what if 1/8, like 12.5% of all of your stuff hashes to the first one, 1/8, 1/8, 1/8, 1/8. It's all evenly distributed. All you've done is take, if you've got 8 million elements in your hash table, all you've done is taken 8 million elements, and instead of having an 8 million element linked list, you have 8 1 million element linked lists. In other words, all you've done is taken the constant outside and cut it by 8, right? Multiplied it by 1/8. All of the linear functionality that you have with a linked list is still there. There's just a different constant sitting out front. So in the long term, collision resolution is not going to sustain you. Eventually, this is going to just devolve into a collection of linked lists, and it's still going to be order n, right? It's order n unless you do something about it, okay? And the thing that you're going to do about it is to rehash things. So we're going to define what's called a load factor. A load factor, alpha, is equal to n divided by m, is equal to the number of elements in the hash table divided by, and then the same m as we were using before, the size of the hash table. In other words, alpha lays between 0 and 1. It's a percent. It's the percent of fullness, right? 1 is it's 100% full. Okay? 0, it's empty. And of course, 0.5 is it's 50% full. And 0.75, that's typically what's used as a default in a lot of implementations. It's 75% full. So that's a load factor. So if when the hash table hits a predetermined load factor, it gets rehashed. Right? Ideally, we'd like a smaller load factor. So one way that we can get a smaller load factor is by getting rid of elements, right? But we don't want to do that because, well, you put these things in here, we're not just going to kick them out. So n is fixed. We can only play around with m. So to get a smaller load factor, what can we do with m? To get a smaller load factor, what can we do to the denominator over here? Increase it. We increase m, I don't know, to some factor, right? In other words, we create a new array, new larger array, and rehash every element. This is just like an array list. Where an array list gets too big, well, that's okay because it dynamically increases its size by creating another array that's larger and copying all the elements over. That's exactly what we're doing here, except that we're creating a new array, and instead of copying everything over in the same order, we're creating a new hash function with a larger m and potentially different coefficients if you really want to, and then rehashing everything. First element over here gets, we recompute its hash value and put it in. Then we do it for every other element. Right? So in other words, rehashing is going to end up being an order n operation. In other words, it's expensive. It's even more expensive than any operation that you could ever do on a balanced binary search tree. That's the trade-off, right? That this is an expensive operation, but hopefully it's an infrequent operation. And like I said before, with my hand graph in the air, it would look something like this. If this is the lifespan of the hash table, right, then, and this is the cost, the cost is very, very small until it starts to get full, right? And then the cost grows, and then at some point you've reached your predetermined load factor, and you say, okay, now I need to rehash everything. That's going to cost you big time. But it brings you back down, and when you start hashing again, right, it looks more constant until it starts getting full again, and then you spike again for your rehash. Right? And then it's more constant, and then spike again. But if you look at the average cost, right, these are infrequent. These aren't order n operations every single time. So because these are infrequent, if you take the average or amortized cost, then it appears to be constant. Right? What does amortized mean? Well, amortized simply means look over the lifespan of the algorithm. Amortized loan analysis. If you take out a loan for $100,000 to buy a house, right? That was a pretty crappy house, but $100,000. Say take out $1 million loan to start a business, right? and you have 30 years to pay that back at 5%. At the very beginning of the loan, you're paying a lot. You're paying $50,000 a year in interest about, right? But over the life of the loan, you're paying it down, right? You're paying down, making monthly payments, and at some point, it's not $1 million the balance; it's a $500,000 balance. And at that point, still paying 5%, you're only paying $25,000. And at the very last month, you're not paying any interest at all. It's just the last payment or something. So if you look at the amortized cost of the loan, very high interest payments over here. The interest rate is the same, but very high interest payments over here, low interest payments over here. You take the average, and that's your average amortized loan cost. Right? Just like this analysis right here. Don't look at the worst case when it spikes and you have to rehash everything. Look at the average across the lifespan of the hash table. And it gives you very, very, very good performance. Right? And not only that, but you can tune this balance factor. Right? What a large, or let's say a high balance factor, translates to poor performance, but low memory. Right? Going back to the beginning here, this is full. Right? We're not wasting any memory here at all. If it were only half full, then we'd be wasting half of our memory. Right? If I want to store 50,000 things and I create an array of size 100,000, well, I'm wasting half of that memory. Right? And so, but if you have a high balance factor, well, you're saving on memory, but you've got poor performance. A low balance factor means that there is less chance of collisions, which means better performance, but more memory, and in particular, more wasted memory. Right? So it's a big trade-off here. If you tune your balance factor so that it's really low, say like a 0.1 balance factor, you are going to be rehashing it every time it reaches 10% full. Now, there's less of a chance of collisions, so there's better performance because you don't have to do that probing over and over again, but you are ending up wasting memory. 90% of your memory ends up being wasted. Right? If you have a high balance factor, 90%, then you get this kind of performance where you've got a lot of collisions and no wasted memory, but lots of collisions, and therefore it devolves into linear search. Okay? So it's a trade-off. This is a time-space trade-off data structure. Right? And like I said, default implementations, like in Java, for example, I think the default implementation in Java has you at a balance factor of 75%. Of course, you can always tune that, and you can create your own hash table and put in your own balance factor if you want. If you can put in a balance factor of 25%, and it changes the performance without changing the implementation. Really, really cool. Right? One thing that I did not address that I'll address in in 1 minute here is what if we allowed deletions? What if we allowed deletions of 100? 100 gets deleted here. But 108 and 116 that couldn't fit there because 100 was there, well, now they can fit there. And so if I come in and I ask the question, is 108 in this hash table? Well, I check. Oh, well, no, that's empty. Right? So it must not be in there, but it is. What are we going to have to do in addition to what we've just been talking about in order to support deletions? We have to use what are called dirty bits. Right? Anytime something occupies a cell, we've got a bit that we set. Right? And we dirty it. We set it to 1 to indicate that at some point, even though the cell is now free, at some point something occupied it. And so it's a dirty cell. It's dirty bit has been set. And so you have to go ahead and do your probing anyway. And if we end up deleting 108, it's even worse, right? That dirty bit was set. All the dirty bits will eventually be set, indicating that at some point every single cell was occupied. And if you want to ask the question, well, does 108 exist? No, 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 no. What did I just do? I just did a linear search. So eventually either it gets full, or if you support deletions, all the dirty bits get set, and you end up having to do linear search anyway. So lots of trade-offs here, lots of caveats. That's why when I say that, oh wow, it offers a constant, amortized constant time operation. That's why it's good in a lot of applications. It's a real workhorse data structure. It's not the be-all, end-all data structure because of all these issues. All right. Any questions? Remember, you have your quiz 2 tomorrow. Again, open book, open note, open computer, covering what we've covered this week. Keep in mind that homework 2 is due on Tuesday, and that is also the same day as your midterm.